Thank you so much for having me here. I really appreciate that. So I'm Hiu-Yung. I'm from San Jose State University. Today I will talk about I will call it simulation augmented machine learning for semiconductor physics and defect discovery. So there is include a few of our papers. So I will give a boring introduction to our school and my lab, but this is related if you are not familiar with TCAD. Then I'm going to give a few examples. I try to organize it, try to show that how the machine learning can behave like a kindergartner, first, fifth grader, and eventually become an expert in semiconductor design. Of course, these are all toy examples, but if they can be realized, it will be a great impact. So San Jose State U is in California, in the Silicon Valley. What's so special about us is that we have a very small campus, but we have 36,000 students. And we are minority serving students. And in electrical engineering, we have about 700 to 800 students. And we supply most of the working force in the Silicon Valley. So what is TCAD? So TCAD is Technology Computer Aided Design. This is one of my major research because I was with Synopsys before for about 10 years. Basically, TCAD is nothing but just a differential equation, system of differential equation solver. You put the relevant physics, Maxwell equation, continuity equation, and transport equation, and you build a structure. Then, in principle, you can solve anything, right? From BJT to process to electrical and optical simulation. The most important thing that we need to know is that you need to have the right model and right parameter. As long as they are right, then we can trust the result. So in my lab, because it is a simulation, we have been working on atomistic simulation for quantum transport, defects in resistive memory, to nanowire simulation, power electronics, including gallium nitride, gallium oxide, silicon carbide devices, and circuit level chip packaging interaction. And more importantly, we also work on radiation simulation on SRAM to study the radiation hardness of devices. So we do some ab initio simulation to get the linear energy transfer and then plot it into TCAD to understand how we can design a radiation robust or hardened SRAM. And our lab also can do some low temperature measurement. Here is a student doing 4 Kelvin. Why this is important? Because we are also working on quantum computing in some of our research. And periphery CMOS that work at 4 Kelvin is expected to be very important to support a large-scale quantum computing. And just as an advertisement for education, I have 2 books. This is for algorithm, this is for quantum computing architecture. I also have a YouTube channel. Please let your friend know if they are interested in this. And at the same time, this one is a little bit relevant to this talk. It is a small scale. We have been working on about more than maybe 20 papers on using machine learning to study semiconductor defects and physics. And we upload the data, preliminary data, to this database. It is not a large-scale one, but I think eventually if we can create a big database, maybe that can help to train a better large language model on semiconductor. And you can try to download the data here. Each of them correspond to a paper, so we have very detailed explanation of the data. Okay, so these are the boring introduction, and now I would like to talk about the motivation of this whole research. The question is that this is so-called current voltage characteristic curve of a transistor. And if you have a very experienced engineer, you measure this curve, you might right away can tell that, well, this one current goes down at high VG, maybe there's some surface mobility degradation, gate leakage, or whatever, right? You see this bump here, maybe you say, oh, there must be a lot of defect in cause trap-assisted tunneling. And this very high current, you may say this is due to gate-induced drain leakage, right? So in the past, if you have a curve like this, even nowadays, you will do failure analysis. You need to find the location, do a TEM and SEM. It's expensive, it's destructive, and you just slow down the throughput, right? So naturally, because of machine learning, we will ask, can we train a machine, right? Like an expert. Then I give them a curve. This is a PIN dial, and they can tell me right away what happened. So what we can do is, let's just create a lot of different dial with different thickness at different region, and we measure the IV. Then we also know the output, all right? We also, what I mean is we also know the thickness and doping of the dial. We train a machine that correlates the IV to the thickness or the structure of the dial. Now, the next time when I do the fabrication, I get an IV, put into this machine. Then I know what exactly the structure is. I don't need to do a TEM or failure analysis. So this will be great, but we need a lot of experimental data. And more importantly, sometimes what we care about is the defect, like what I just said, the location of the defect that causing the trap-assisted tunneling, etc. You cannot control this precisely in experiments, right? So the best is we can use TCAD. The best is that we can use TCAD or simulation to do the troubleshooting and failure analysis. Because for every new technology, as we know, when you are not mature, at that time you actually don't have a lot of experiment. The number of data you can use to train the machine is limited. But when it is very mature, the defect U, the U is very high. You don't have many defective data unless you deliberately do it, right? So you see that the defective die will reduce. So number of defective data that you can use for machine learning is not much. And that's why TCAD or simulation is important. But very important is that you need to have a well-calibrated TCAD, as I said earlier. This is a very good tool, but garbage in, garbage out. Similarly, can we use SPICE for the same purpose? This is one of the idea. We can, because SPICE is very fast, we vary the parameters. For example, how about we add a contact resistance to a MOSFET and put in a SRAM or inverter circuit? We build a machine learning model, right? And then during the measurement, you just probe the wafer. You can use the machine learning model to inverse or to deduce what are the contact resistance of that inverter. So in the past, you need to do failure analysis. Now with some preliminary metallization, you can extract the contact of each of a complicated circuit. And at the same time, you have many different process maps, like the uniformity of the CD, the thickness of the oxide edge. Maybe for one of them, you find a high correlation. Then you know right away which step is causing this contact problem. So again, the idea here is that you pre-train or pre-simulate to generate a lot of data using simulation to build the model that you want. So that is the motivation. So let's start with a naive example that we studied in 2018 or 19, right? So it's a PIN dial. So what we did is that assume that we are interested in knowing the thickness variation of a process. This is a simple PIN dial. So you may have thickness variation in the N region, the intrinsic region, and p-type region. And then you measure them, we generate 2000 curve and get this group of IV curve, right? We need accurate model. So in the following slides, because this is not really a TCAD talk, I will just skip those TCAD. I'm not going to in-depth for the TCAD, and you are all machine learning expert. I will not spend too much time on discussing how the data are generated, just to give you the idea and also the result, right? So we generate a lot of data. Each curve will correspond to different thicknesses, right? And then we will train a machine. And definitely, you all know that it is very important to determine if we need to do some data preparation. For example, in this case, we need to do some transformation because what I'm showing here is the log scale, right? So you can always think about this like a kid, a kindergartner. You tell the kindergarten, okay, for that thickness, you get this curve. For this thickness, you get this curve. Now I get this curve. What is the thickness? If you put in the linear scale, this is basically 0. The kid will say, well, any of them, because they're all 0. But if you want to distinguish, you need to put in log scale. So here show that if you try to pre-process it to log scale first before you do the training, the prediction is much better than the linear scale. So here we just show that if you have the right data, it turns out that you don't need very fancy machine learning tool, right? Just a simple linear regression can do very well. It can predict the thickness of the intrinsic region well, right? Now, I have not told you that from device physics, the leakage here depends strongly on the intrinsic thickness region. And that's why it did very well when we train it with those data. But it cannot predict a thickness too good. For example, of other region too well, right? For example, for the at the 2 volt or at the negative to 0 volt regime. Okay, so here show why this is important, because for a PIN diode, the forward current will be the resistance of the thickness of the N region will dominate the on current. So it can learn from there just like a kid, right? But when you try to give the reverse region and ask it to predict the resistance of the N region, it won't, because that region is dominated by the intrinsic thickness region, not the thickness of the N-plus region. So we should have the relevant physics to be captured during the data generation. So another trial is that what if we only change the doping concentration of this region? Now we see that besides we have a big variation in the reverse part, we also start seeing variation in the forward part. If you put it in linear scale, you see that for different doping level, we get different forward currents. So just now I said that we cannot predict that well if we just use those curves, but now with this doping, let's see what happened. Indeed, we were able to predict them well. Let's ignore this curve because of time. But basically here, the bottom 2 curves shows that I can predict the thickness, the doping of the N-type and P-type region very well. Now, if as you know, in device physics, the on-state current depends on both the N-type and P-type region resistivity. So here it predicts well. It means that it even can distinguish whether the resistivity is due to the N-type or the P-type. For a human, you cannot do that at all, because basically higher doping is just lower resistivity for N-type and P-type almost at the same time. Then why? So we try to do a plot on the curve that one has a high N-type doping, low P-type doping, another has a low N-type doping, high P-type doping. We do see that they have a different shape due to different mobility model. So it means that the machine was able to capture all these details that a human cannot learn easily. I will skip these slides. This is just for the intrinsic region, not very important. No, so at this stage, some people may be laughing at our research, right? Will say, is this so good? But at least now we show that TCAP provides a cost-effective way to generate the IV and CV for machine learning. We show that it correlates IV and CV to the structure or defect, right? Thickness, doping variation, a defect, information very well, right? But we also show that you cannot learn more than the data contain. Everything is just very normal, like how we train a kindergartner. Okay, but we're using simulation data to predict simulation data. Of course, there's unseen simulation data, but how about experiment? So the next step is, okay, now let's apply this to a Schottky gallium oxide Schottky diode to see if that will work. Okay. So a brief introduction is this so-called Schottky barrier diode. Gallium oxide is an emergent material. This is a wide bandgap material. It is cheap or have a low manufacturing cost for the substrate, so that it is that's why it's pretty promising compared to diamond, silicon carbide, and gallium nitride. But actually, because it has a much higher band gap than gallium nitride and silicon carbide, so this one is promising for ultra wide bandgap material also. Right? So it is a Schottky barrier diode. Basically, everything is N-type, and the bottom is the ohmic contact. The top is a Schottky contact with nickel gold. So this formed a diode. Okay, so this is fabricated by our partner at that time in Virginia Tech. So when doing the fabrication, because it was pretty novel, so it's difficult to fabricate. You have doping variation in this drift region. You have thickness variation in this drift region. And at the same time, when we are fabricating the diode, they deliberately perform some chemical treatment before metal deposition. So you have a different work function also, effective work function, due to the interfacial state. But they also measure it at various temperature. So we get a bunch of data that is a result of different thickness, different doping work, different measure at different temperature, different work function, different doping and thickness variation, right? So our idea is that, okay, now let me do a TCAD simulation. And we work very hard here at San Jose State U. We spent 2 weeks to generate 150,000 TCAD simulation for this structure. And then we build a machine. And then we feed in their data and try to predict the work function, the temperature, the thickness, and the doping variation in that structure. Okay, here I will do it quickly. The only message with what we try to do here is just that our simulation is very accurate. We calibrate the carrier concentration and mobility model well to other experimental data. We calibrate the forward IV and reverse IV well to our experimental data. And we perform a 2D symmetrical simulation, which is equivalent to a full 3D simulation with self-heating. And this matches the experimental data very well. So we trust that our TCAD calibration and simulation are good. So what do? We continue the Naïve way what we did. We discretize the current, and at the same time we also put in the delta of the current, which represent the slope, right? Because we discretize the interval evenly. So the change of the current is just proportional to the slope. So we get the slope also, not just the number. We did some polynomial generation to have different order and do linear regression to the curves to get these 4 parameters. Okay, so nice, just like what we did before, like a kindergartner, learn everything very well. And we apply this to the testing data. Again, they match the simulation, the actual value very well. Again, what we are doing is that we put in the IV simulation IV curve, correlate it to the structure or defect parameter. We train the machine, then put in new IV curve and ask it to predict what are the temperature, work function, etc. And they are perfect for this 150,000 data. Okay, so this looks a good machine, right? Then we put in the experimental data. Now you see that experimental data vary a lot. It was also not well measured because it measured at high voltage, high current, and also it was a novel material. You see all these cane bumps, which are not realistic. And let's also look at the comparison between the TCAD simulation. We calibrate 1-to-1 of them, TCAD simulation and the experimental data. For a human, you will say this is perfect. Oh, nice job, right? But there's some difference here, but as a human, you say, wow, this is just because of noise, right? Your TCAD is perfect, right? But you do get noise in the experiment. So now we ask it to predict. Now, as you can see here, we try to predict the 4 parameters. We put this -9, as the expected range. For example, the thickness should be between these two blue lines, or the temperature being measured is between 300 Kelvin and 500 Kelvin. The work function should be this. And then we also put the, I'll talk about this black dot later. And then we use the machine to predict it. Now you see that it actually gives some very absurd data. It predicts the thickness can be as thick as 1 meter. The temperature can be as low as negative 100 Kelvin. Work function around doping can go to 10 to the power 22. So why is that? That is just because we train a machine that is too arrogant and naive. Like you tell the kindergartner, memorize everything, and yeah, we train it with all this simulation data. But once the kindergartner saw this bump here, the student got lost. I never saw this before. And it was so arrogant and confident and think that the model is correct. Then in order to fit this part, you need to predict something that is completely wrong. So it means that what we have been doing was not good enough, right? So because of this, then we think that, well, we should teach it to learn the principal component. So we use some principal component analysis to get 4 principal components, because we know that all these IV are changed based for 4 variation in the simulation. We only vary the temperature, work function, etc. to generate this IV. So whenever we get a IV, we try to get the principal component before we do all this polynomial regression and polynomial generation and linear regression. So with that, we get this black dot. And now you see that they are all within the range, because they now learn not just to memorize the IV curve, they start to understand different features inside when we do the principal component analysis. More importantly, we did not inject domain expertise. This time we even did not put in the slope to there. We let it to learn itself. Okay? And we also try to predict the temperature and work function. At least now it's not junk. We have some weird points, but overall looks better, but not good enough. You start seeing that particularly. Let's look at the range of the temperature. Supposed to have a range of 100 Kelvin, 110 Kelvin. This one only predict about 50 Kelvin. And you see that we put relative experiment temperature is because it cannot predict the absolute value either. Similarly for the work function. Okay, so by using principal component analysis, right, we don't need to use the domain expertise. It avoids overfitting and overconfidence, right? And we can do some pretty good job with the experiment. But this is not good enough, right? So can it learn the physics, right? But before that, since we now realize that they are too arrogant, so maybe we can make it more humble. How can we make it more humble? More humble is that you need to make it know that what you're learning might not be true. So that is what we're doing. We go back to the PIN file. We have 3 sets of data. The first set is the thickness variation again. The second set is doping variation that I mentioned earlier. The first set is completely different. Okay, so we trained the machine, use the one that we had earlier. Again, in the training, everything was perfect. But you ask it to predict the other set. The first paper, what we did was to use the same set of data to predict the same set, although predict the unseen IV curve. But here we try to predict other set. And you see it predicts something, again, completely wrong. Very large thickness, negative thickness, etc. So what we did is that let's add the noise to the data. So we try to have different signal to noise ratio. So for the curve that we have, we add some noise. So then now the student will understand, hey, there's something I don't understand. I better just look at the trend of the data, right? So with this, now it can predict it pretty well. Firstly, they are reasonable. Secondly, the mean that they obtain is very similar to the mean that we have in those data sets. And different signal to noise ratio have different results. But as you can imagine, if you have a larger signal means smaller signal to noise ratio means you have a larger noise. During the training is worse, right? just the exam is worse. However, overall, the student did learn something, you get better results, right? But if you have less noise, you have a better fitting during the training, but then the real prediction actually is not as good. Let's go back to the gallium oxide data. We do the same thing, which apply to noise to it. So this is the linear scale of the IV. This is the log scale of the IV. We apply some noise based on a Gaussian white noise based on signal to noise ratio at each point. And now if you look at this, without noise, that is what I showed earlier, but plotted differently. You get very large temperature, 10 million Kelvin. Right? With noise, now you see that we have a very good distribution. Particularly, the range now is good. 100 and about 100 Kelvin, the range prediction is also 100 Kelvin. Still, we are still putting the relative because it's still not good enough. But the point is that now we improve. We know that we add some noise can avoid the overheat fitting to make it more humble. But if we just make it more humble, right? Can we make it more knowledgeable, right? So with that, we start using autoencoder, right? See if we can learn the latent physics. So I think you are all expert, but let me just quickly say, you know what is a neural network? An autoencoder is just a neural network. You have the same input and output number of nodes, and then you constrict the middle to very small. So basically, if I have 102 data points, I want to reconstruct it so these two are the same for a training process, then it means I have captured and coded the information with only 3 of them because I put in the curve, eventually they're captured to here, and then I can expand it back to the curve. So this is like an encoder and decoder fashion, right? So we try to constrict the middle to a fewer node and hope that we can capture the physics. And this is a BC diagram. We don't need to fully look into it, but the main idea here is that we try to use autoencoder, the PIN dial, we discretize it to, let's say, 52 points, so 52 IV, right, for some scaling. So in the autoencoder process, we reconstruct it, right, we train it so the input and output IV are the same. Then we only have 3 hidden nodes. So then it means I capture this 51 dimension into a 3 dimension. And we think that this is possible because all these IV were generated by only varying 3 parameters, the thickness in the P region, intrinsic region, and the N region. So we do the same thing. We do the same thing for the log scale part also. But more important is that now we have this hidden region, right? This hidden latent space, we call it latent space node, we regress it, this H, against the label or the actual physics that we have put in. So it means that once I get this hidden region, I can just go through this linear regressor and predict the thickness. Okay, so again, we use different thickness to generate the IV. We capture the latent physics of this IV to 3 parameters, and then we relate this 3 parameter to the thickness. Then if you give me any IV, I go through this autoencoder to get the latent variable, and then I go through this linear regression to get back the thickness. Because we think that through this process, it will learn the physics. So we repeat the same thing, right, with 2 sets of parameters. Again, if I use linear regression, everything is wrong, I have negative thickness, etc. Here we did not apply the noise, but we use the autoencoder. So we train with the first set of data and try to predict the second set. Everything fall within the range. Still, we get some negative value, but overall, it is much better. And the reason we get negative value is that, as we said earlier, it's difficult to separate the N region and P region, even for a human, because they all contribute to the IV very similarly. So we should actually predict what is the total thickness and the intrinsic thickness, and they give very good results. So that is the introduction to autoencoder. So now, so we show that autoencoder is good. We believe autoencoder can capture the latent physics, right? But how good is this, right? So is it as good as a device expert? Now then we apply this to the gallium oxide data again. Now first we try to use domain expertise. If you want me to tell you what the measurement temperature is and what the work function is for a diode curve, I can do it easily because I just need to plot in log scale, look at the subthreshold slope. Because the so-called subthreshold slope is just how fast you turn on a diode. And it's telling me how much voltage I need to apply to get a 10x increase in the current in this subthreshold region. Okay, so I'm a device engineer. I know this is proportional to KT over Q. So all I need to do is just find the slope. And if you want me to know the work function, extract the work function, I can do it also, right? Because all I need to know is find the shift of the curve. So as a device expert, I can extract the subthreshold slope easily. I can extract the voltage at which it gives a certain current. I call it V0. So I do this for every curve in my training. So I have many training data, 150,000, right? So I can extract this data. Then I just do a simple neural network and ask it to give me the temperature and work function. And with this, I can plug in the experimental data to find the temperature and work function. So that is the domain expert. Another way is I don't do anything. What I do is first, I put in the IV curve, I add some white noise to it. And then I use autoencoder. This autoencoder will reconstruct the IV curve from input to output. But my goal is just to capture the latent physics. So I constrict it to 2 nodes and then regress it against the work function and temperature I used to generate the IV, right? And then now if you give me the experimental data, I just put in here, automatically add the white noise, go through the encoder, go through the regressor, and it will tell me what the work function and temperature is. Here shows the IV, training IV, here shows the noise that we apply to it. So anyone can do this. You don't need a device physics or take a device class before you can do this. And here shows the result. So you see that first for work function extraction. Now, without domain expertise, with domain expertise means the one that I extract the V0 and subthreshold slope, a device expert, you get all this black dot. We expect a straight line. Now you see that this is 1-to-1 correspondent. It's a 45-degree line. Now, if I just use the autoencoder, but I don't add the noise, I get the blue lines. Actually, it's really not bad, right? I think, in my opinion, right? Because we did not inject any device physics there. But what if you add noise? And it is even better. It becomes the red dot, right? So it has a very similar performance as the device expert. How about for temperature prediction? Is it the temperature at which we measure it? Now, without domain expertise, we actually do not do too well. The green one, the dotted line are the expected range. You see that it actually has a range that is too fast. The one that was the measurement conduct near room temperature actually was lower, right? But when we use autoencoder with noise, it actually give a better result in this sense. So at least sometimes you can even perform better than an expert, right? So it can, in this particular case, I need to have a caveat. If it becomes too difficult, I don't know, right? It can be a device better than a device expert. So we further expand this just for a circuit. So I need to say that our students are very good. We want to study this inverter. So the scenario is that, okay, now you have microfabrication, and you have some test structure on the squad line. People will keep testing them during the fabrication process. And you can put a simple inverter there. Now, what if you have contact opening problem? Then it means you have a contact resistor here, right? So can I actually train a VTC of an inverter with different resistor here? And then later I put in any VTC I measure, and it can deduce what are the contact resistance that I have in that circuit, right? And that was during COVID time, and we don't have the equipment. And also it's impossible to do fabrication, because imagine that I need to put different resistor on the wafer. It's going to be very expensive and difficult to measure. And then COVID time, our school gave our analog circuit class, which I was teaching. Each student, they give this analog device, ADALM 2000. I got a copy also because I'm instructor. I need to develop the material, right? And my TA also got one. I say, okay, so since you have this, do you want to try this? You try, just use the discrete component and then connect this to the resistor and do the measurement. Now this is a plus. It's not accurate. It has a lot of noise, as you can see here. But the good thing is that we're going to show that even you have noise, we can predict it well. So what we're doing is this, okay, we change the contact resistance and also the NMOS to PMOS ratio here, right? So that, for example, we have 3 or 2 or 1 PMOS, right? And then we do the measurement, right? So you get different VTC, V in versus V out. We also do the simulation. The simulation had the device model calibrated to the experiment, right? So you get different curve. Here only show a few of them. Simulation are really perfect, 3 and 0, and here you get a lot of noise, negative due to overshoot or measurement error, right? So again, we use autoencoder, right? We train it, and then we reduce it to 2 nodes, and then here show the input output. We try to match them, so you train the machine and regress it against the resistance. And now, then we put in our experimental data, which is noisy, measures by some low-grade equipment, but you see that it can predict the resistance we put in the experiment pretty well, right? However, we need to do some, we can only predict the relative ratio to the MOSFET, which is okay, because in reality, we know the resistance of the MOSFET, but it works well. And another message is that if we try to plot the hidden value in color, right, against the 2 resistance we put there, it's interesting for different ratio of the PMOS to NMOS ratio. So the ratio, what I'm meaning is that whether we have 1 PMOS to 1 NMOS, 2 to 1, or 3 to 1, right? You see that they have similar pattern. If we plot a resistance value to the hidden variable, they also have a similar pattern. We are not able to explain this, but this makes us confident that they really learn something in the latent space, the machine. Okay, so we have done this to the autoencoder, to the circuit also. That's why in the beginning we claim it's TCAD augmented machine learning, but we believe simulation augmented machine learning can be used for everything, right? Because of time, maybe I want to skip this part. This is just another autoencoder we apply to 3D device, which works well. But let me talk about inverse design. So can we do something now is really better than device engineer, because doing inverse design is difficult. So I'd like to give a scenario, right? The circuit designer in a semiconductor foundry, right? They always bully the device and integration engineer. They will come in on Friday meeting and say, hey, your device is not good. I just hand draw a curve. Give me a device like this, otherwise we cannot make the circuit. We will fail to deliver the product. So what can you do? You work very hard in the weekend to experiment or run TCAD simulation, and hopefully to come up with a device that will give this curve. Right? So the question, and this is the PIN diode that I mentioned earlier. Right? So the question is, what can we do? Right? So let's say they only have the freedom to change the thickness of the intrinsic region and total thickness of the NMOS and PMOS. then you can use TCAD simulation to do that, right? But if you are an expert, assume you were working in this industry for 10,000 years, you have seen all the different nodes. When I say 10,000 years, I really mean 10,000 years, although the semiconductor industry does not have. Through all these 10,000 years, when you see this curve, you probably will tell the circuit designer right away, no, it cannot do this. The physics doesn't work if you have a silicon device, right? But can we have something like this? Like what if the circuit designer just came back and give you another 13 curve? Come up with something, we need this in order to have a good device, in order to have good circuit, right? And then now you don't need to work for 10,000 years, even just study the physics for device physics for 1 year, you know that. No, this blue curve and red curve just doesn't work. You're asking for something that has very narrow band gap, something has very wide band gap. It doesn't work because we're doing silicon. But how about for this? You don't know. How about for this type of leakage? You really don't know, right? So what we try to do is then we use the autoencoder. The autoencoder will learn the device physics, and then what you do is that you just put in this hand-drawn curve to the autoencoder. Remember, what we did earlier was that you use simulation curve to train an autoencoder that can capture the PIN thickness. So you put in experimental data, it will tell you what the PIN thickness are for your device. But it is the same. Now I say I want to have this curve as the experimental result. Then you should tell me what PIN thickness should have in order to get this curve. So for this 12 curves, you see that the autoencoder was able to predict what the thickness should be, and then we use this thickness to do a TCAD simulation. It's just like that you do a fabrication to verify it. First of all, I would say it is pretty good. First, look at the leakage. They track pretty well. There are many orders of difference. And secondly, you might say, well, your forward current does not fit well. But the reason is very simple, as I mentioned earlier. The curve they drawn is impossible for silicon, for the mobility that we have. And that's why this actually can help us to tell the circuit designer, no, this doesn't work if you try to draw in this way. No way, unless we move to high speed or add string to the silicon, right? Another thing is that it is brave enough to tell the designer, you need this curve, but no, the forward current is, the turn-on voltage is too large. That is not the system that we want. The best I can give you is this turn-on curve, okay? So that's for inverse design. And this one I won't go into much detail, but just want to tell you we can use a similar concept on image. So what we did was that we generate many data, many TCAD data, and we convert it into images. So we have different transistor. This transistor has different gate length, different poly thickness, different substrate thickness. We can use a variational autoencoder to capture the physics or the latent space of these images. So images are changing just like the digit recognition, but now this is just a transistor image. At the same time, we have the corresponding curve, IV curve of each image. We also train them. And then, of course, the corresponding one should have relationship to this one. So we perform a linear regression between the latent physics of the image and the latent physics of the curve. So that means if you give me any hand-drawn image, I can predict the IV curve because it finds the latent physics of the image, find the corresponding latent physics of the IV curve, then it will do the decoding and give me the curve. And similarly, you draw a curve to me and say what transistor can give me this curve. Find the latent physics of this curve, then find the latent physics of image and do the decoding, and it should give me the image of the curve. And let me skip this. And that is what we did. And as you can see, that is if we put in the, we put in the current and then ask it to predict the image, then it can do that, right? Sorry, I'm a little bit lost. Yes. Is someone talking? Okay, so yeah, so this will be the last one I have. Rushing a little bit. This one I just finally the last one we'll talk about new some of our newer study. So as a TCAD engineer, we always want to do parameter calibration for novel devices, and this one we use the gallium oxide again, and we try to use the physics informed neural network. Although it is a little bit simple, again we have this gallium oxide Schottky diode, and our goal is that this is a novel material, so we don't have the parameter for the Philips Unified Mobility model, right? It's very complicated. So earlier in my slide, I showed you I did a very nice calibration. I emphasize that I did it, not my student, because I want to say that I have TCAD experience for 10 years or 15 years, and I got my PhD in device physics, and it took me maybe 1 month or 2 weeks intensively to calibrate those data to the experiment. Now, the question is, can you do it by machine, right? So this is the example we want to do. So now we have 7 parameters. We have this mu max, mu mean for this equation, reference T, and at the same time the measurement, the temperature of the measurement, and also the work function. 7 parameters, right? And another thing that I think is important is that we don't request the experimentalist to come up with a 4-point probe measurement, a structure, a test structure that you measure the mobility, so that we get the mobility exactly. We still just use a device that was fabricated, but that device depends strongly on the mobility because of this drift region, right? Can we calibrate it? So again, we use a similar concept. We use TCAD to generate a lot of data, but this time we change the parameter of the TCAD. So different parameter give different IV. We go in this autoencoder. This have 10 hidden nodes, right? This is the autoencoder. And then we, in principle, we just regress this hidden node against the 7 parameter that we have. But this time, we do the same thing, but at the same time, we try to inject some laws for the physics. And this laws is pretty simple. It just requests that this mu mean needs to be smaller than mu max, right? So just because of the physics. And then we have this framework. Then if you give me the experimental data, we find the hidden physics, and then we go through this PINN to find the 7 parameters. And once we get these 7 parameters, we can do TCAD simulation to verify, because the so-called calibration is what? You find the right parameter, and if you do the TCAD simulation, you can match the experiment, then you finish the calibration. And these are all the experimental curve, right? And we did very well. For the manual one, first we look at the number that we have, that we extracted for different parameter. For the manual one, it is this, right? If we don't have the neural PINN, just a regular neural network, it's just okay, but some of them, particularly this one, is too large. But if we inject the PINN, they are closer. But it doesn't matter what value you got. The most important is if this value can predict the experimental curve. So here we compare the R score, just the discrepancy between the experimental curve and the TCAD simulated curve based on the extracted parameter. The manual one is like this. Some of curve do not predict well, because as I showed you earlier, we have some big noise, right? Because the curve itself is wrong, right? Due to noise in the experiment, right? If you don't have PINN, we have many curves that do not go predict well. But with PINN, it have a very similar performance as the human expert, that's me, right? Yeah. Okay, so I think I will stop here. Basically, I show you what we have done, and we always look for collaboration. You can see that for so many studies, we are using only 2 experimental data because we don't have enough experiment, and one of them was just a blackboard, right? So if you have experimental data or even ab initio data, right, that would be very useful. And we need to acknowledge the support.